Welcome back to the channel. Before we get started, a quick word about ECAS. ECAS offers free downloads on a variety of measurement and control topics, giving you practical resources you can use straight away. It also provides courses covering many elements of instrumentation and control, designed to help you build your knowledge step by step. With this video, there's a free download available, and you can find the link for that in the description below.
If you work with level measurement, you've probably seen a capacitance probe. But if you don't understand the core formula behind how a capacitor works, you are guaranteed to miscalibrate and misdiagnose this critical instrument. This video is the ultimate crossover. We'll show you the essential physics of capacitance, how the level transmitter uses that exact formula to measure product, and the three most common failures caused by product coding and density changes. Stay until the end, because the relationship between product temperature and dielectric constant is the key to mastering calibration. Let's start with the fundamental physics. A capacitor is simply two conductive plates separated by an insulating material called a dielectric. When voltage is applied, the capacitor stores electrical energy by building up an electrical charge on these plates. It blocks direct current, or DC, but allows alternating current, or AC, to pass, making it a crucial component in nearly every electronic circuit. The capacity to store energy, or C, is defined by a simple formula, C equals epsilon, multiplied by the area of the plates, divided by the distance between the plates. This relationship governs everything the capacitor does. In general electronics, capacitors are used for three essential functions. First, energy storage. Like a very small, fast battery, they can release a quick burst of power. You see this in camera flashes or in filtering circuits that prevent sudden voltage drops. Second, filtering. This is vital. In DC power supplies, capacitors are used to smooth out the ripples and noise in the signal, ensuring that sensitive microprocessors and sensors receive clean, stable power. They are the guardians of signal integrity. Third, timing. Since a capacitor takes time to charge and discharge, engineers use them in conjunction with resistors to create time delay circuits, such as setting the blink rate of an LED or the timing for a motor start sequence. The design factors the capacitor's value is defined by three physical factors: area, distance, and epsilon. If the plates get bigger, the area increases and capacitance goes up. If the plates move closer, the distance decreases and capacitance goes up. But there is a third crucial factor, epsilon, or the dielectric constant. Epsilon represents how well the insulating material, the dielectric, can store energy. This factor is absolutely essential to understanding the level transmitter. Air has a dielectric constant of 1. Water can be as high as 80. Now let's look at the transmitter. The level transmitter is nothing more than a giant, specialized capacitor. The conductive probe rod acts as one plate, and the metal wall of the vessel acts as the other plate. Look back at the formula. Capacitance equals epsilon times area divided by distance. In a fixed tank, the distance between the plates, D, and the effective area, A, are fixed and constant because the probe rod and the tank wall never move. This leaves only one variable left to change: epsilon, the dielectric constant. Here's the brilliant part. When the tank is empty, the space between the probe and the wall is filled with air, which has a dielectric constant of approximately 1. This gives you your minimum capacitance reading, or your 4 milliamp signal. As the product fills the tank, the space between the plates is now occupied by the product. If the product is water, the dielectric constant changes from 1 to 80. This massive change in epsilon creates a large, measurable change in the total capacitance. The transmitter converts this change in capacitance into your linear 4 to 20 milliamp level output. The measurement relies entirely on the dielectric difference between air and your product. Now for the essential troubleshooting knowledge. The system only works if it can rely on stable values for the plates and the product. There are three common failures technicians see in the field. Failure 1. Coding and buildup. If the probe develops a thick, conductive coating, say from sludge or sticky chemicals, the effective area, A, of the original plates is altered. This causes the baseline capacitance to drift, leading to a permanent offset error. You must clean the probe regularly. Failure 2. Product change. If the plant switches from product A to product B, the dielectric constant of the medium changes significantly. You must perform a full level calibration, as the transmitter is measuring epsilon, not actual level. Failure 3. Temperature errors. Since the dielectric constant of most products is highly sensitive to temperature, a large temperature swing in your process can cause your level reading to drift, even if the actual product level hasn't changed. So there you have it. The Capacitance Level Transmitter is not magic. It's a brilliant application of the simple physics formula capacitance equals epsilon times area divided by distance. Understanding that the instrument measures changes in the dielectric constant, epsilon, is the key to accurate calibration and fast troubleshooting.
Thanks for watching. I hope you found this video useful. If you did, don't forget to hit the like button and subscribe so you don't miss future content. I'd also love to hear from you in the comments. Let me know what topics you'd like me to cover in future videos, or drop any questions you have. And remember, ECAS doesn't just offer free downloads and courses. We also provide consultancy for any instrumentation and control engineering problems, whether you're an individual technician or a company looking for solutions. With this video, there's a free download available, and you'll find the link in the description below. See you in the next one.